I'll start off by saying thanks everyone for joining us today. This is the sixth in our series of talks about the Agricultural Conservation Planning Framework Toolbox. We have one more to do a wrap up, but we're saving previous presentations as YouTube videos in our Ohio Ag website. You can find the link there. I think Steph will send that out, a link to that at the end. But we'll start right in on the ACPF Toolbox, as we call it, is a collection of tools developed by the USDA, written primarily in Python. It's based on the Esri platform for the most part, using either ArcGIS Pro or ArcGIS Desktop. It requires the use of the ArcGIS Spatial Analyst extension. It does also take advantage of some open source tools that were written at Utah State called TAU-DEM, and they were designed to help identify locations that met the criteria for siting as developed by the USDA NRCS. So this is a collaborative or a cooperative project between the Agricultural Research Service and the NRCS. And it's available for free as a download at the website we'll see at the end. But the main point or idea behind developing this tool was to try to identify locations that were suitable for various practices that could be identified by using GIS. In order to try to identify those locations, they had to sort of categorize the practices into certain types and then try to deal with them in a consistent fashion. So there are a few ways of looking at this, but the important point to start off with is that the tools themselves don't exist in a vacuum. The assumption is that the Watershed team of local stakeholders, the soil and water conservation officers, local ag producers, crop consultants would participate in a process that would look at things like 4R, soil health and conservation planning on the farm at a field scale, and also in a process that would try to identify conservation objectives for the whole watershed. So in ACPF, we've used the 12-digit HUC unit as the planning framework. So all of the ACPF runs that we have done and are being done are at the HUC 12 scale. So specifically in the ACPF Toolbox, though, there are, and this is sort of my way of thinking of this, three ways that the practices are applied for two different purposes. So there's tile drainage, which I'm just going to assume that everyone understands that what tile drainage is, subsurface runoff, and then surface runoff. And we can sort of lump those ways of dealing with that into in-field practices, below field practices, and what I call along field practices. So there is a variety of these types of practices, all designed to try to help deal with water quality and water quantity issues that may be faced by the watershed that we're talking about. And there are specific NRCS practices that these tools were designed to develop suitable sites for. We've talked about grassed waterways as an infield surface runoff tool. We've talked about riparian buffers as a long field surface runoff tool. And we're going to talk today about a below field tile drainage practice. And that specific practice is what they designed this tool for, but I like to think, and I don't know if this is true or not, but it ought to be true that in addition to this specific practice for denitrifying bioreactors, this similar process could be used to identify for phosphorus reduction practices, like filter beds that have different medium in it. We'll talk about that in a second here. But denitrifying bioreactors are, I've come to think of them as like a big appliance that you attach to your tile drainage network. It's really pretty low tech when you think about what's involved. You put water control structures on two ends of it. You dig a big trench in the ground, not too deep, and line it, fill it up with fairly clean wood chips, and then cover it back up. And because you did a lot of math that's specified in the technical guides, you'll know exactly how much flow can be treated and how long the residence time of the water in the actual bed is. And you'll be able to basically get a pretty good handle on how much nitrate is processed by the bacteria that thrive in the anoxic conditions of the bioreactor bed. Basically, the bacteria transform the nitrate into nitrous oxide, a gas, which is then vented off. So it removes the nitrate out of the water so that water that flows out of the treatment bed is, there's been a lot of research done on this. There's a lot of depends in this. There's many variables like temperature and the size, the sort of arrangement. So those things impact what the actual reduction of nitrate is, but it's significant. And the design standards aim for a 30% reduction, but I've seen statements of 50% reduction or more. This is as I said, a low-tech practice, but it's not a permanent one. The design standard calls for a 10-year life of effective reduction ability, but the outer limit of it is still to be determined. Some people are saying that it may go 20 years. Some people say 15. So I'm not really sure on that, but eventually it will need to be recharged. Basically, you would have to dig it up and redo it with fresh chips. But as far as these things go, this is a pretty easy to implement practice. Now, ACPF is a way to look at the landscape and find a profile that matches the profile that's specified in the standard. So for bioreactors, we consider the hydric soils, the slope, the area of the contributing drainage, and the surrounding land use. Those are the major factors involved in this. I will say that in terms of slope, the tool doesn't know whether a field is tiled or not. The tool assumes that any field that is, I think, a mean slope of less than 5% is going to be tiled. And in Ohio, for sure, in most of the upper Midwest, I think that's a pretty safe assumption by this point. Tile drainage is a very widespread practice. in the glaciated part of the country. ACPF uses a set of standard, widely available data for the most part. It requires the use of a high-resolution elevation model. In Ohio, we use LiDAR that was developed by the state of Ohio, but the tool also allows the use of the GSERGO soils data from the USDA. It actually fetches it for you so that you can use it along with the Agricultural Services Cropscape data, which it also downloads. And then you can provide ancillary data like roads and streams that you can get from your public GIS sources. But the first thing and the crux of the whole project is the hydroconditioning of the digital elevation model. And this allows us to model the way the water moves across the landscape so that we can try to identify areas where water is more concentrated, like streams and ditches and swales, and also hopefully places where the flow is impeded, like depressions, wetlands, and ponds. Now, for this specific practice here, the toolbox identifies locations in a field that have at least 20 acres up to 100 acres of contributing drainage, 10 of which have to be in the specific field that's being considered. The tool also tries to identify a location for the bioreactor by estimating the contributing drainage and then taking a fraction of that, half of 1% of that size, and settling that in the spot where it ought to be placed. The tool tries to avoid areas that are exceptionally hydric, greater 90% or greater hydric soils in the contributing area, because they don't want to put the bioreactors into an existing wetland. We need to have the water flowing, and that would defeat that purpose. And there are many things that the tool can do, but it can't do everything. So there are specific things that need to be estimated once you get to a field that can only be done by a human, a drainage engineer, or somebody who has a better understanding of the tile drainage network and the soils. So this is the first pass at a suitability estimate. Now, one of the great powers of the ACPF Toolbox is that it does use the full power of GIS to allow you to see things that aren't readily apparent. This standard watershed that we've been using in all of these all of these presentations here. But you can see some various land uses. There are some forest areas. There is some agricultural fields. There's houses, barns, roads, and streams. But when we look at the elevation model, for example, we do start to see that there are some areas over, like in the upper right, where the elevation is a little higher, and then in the to the west or to the left of that, where the stream runs through, where it's lower and possibly flatter, we're not really sure, but all of that water drains down to the lower left-hand corner to the southwest. But that in itself is useful, but not sufficient. So one of the things that the tool does is calculate, based on those 2-meter elevation models, pixels, what is the percent slope or percent change in slope for each of those cells, and then displays it. I've done it here in a classified setup where we can start to see some of these areas are quite flat, right? 0 to 1% in the purplest color, and the second highest class is 6%, and there's not much of that. So we start seeing stream banks and some other improved areas that have steeper slopes. But for the most part, the majority of this landscape is less than 6% slope. But a continuous layer of elevation change isn't quite what we need. What we really want to be able to do is look at how are the fields and how sloped are the fields. The tool will go through each of these field boundaries, which is a data layer that you provide to the tool, and sum those continuous percent slope values and establish the mean slope for the specific field. So we know that drain tiles are generally focused on draining, field by field, so that we can start to get a handle on which fields are flatter and which are less flat. And then we can go through a process that kind of convoluted, but will allow us to establish some values that will help us identify places that, should they be in need of nitrate removal treatment, we can know that some of these are bigger opportunities or some are smaller opportunities, depending on the field and the needs of the producer. This is important in the sense that these practices are technologically simple, but they're not so simple that they're free. So there is a cost involved with the installation, not really so much the operation, but there is support available through the NRCS, but there is also a cost share. So we being able to sort through these and say, for example, this one in the upper left here, acres treated 79 acres, acres used 0.39 with a mean hydric percent for the field of 25%. So the process that's used in doing this is pretty neat, but the first step is to identify the lowest point in the whole field. Then make sure that it's the lowest point heading out, that water is actually draining at the outset, or it is the lowest point where water is leaving the field. Then we sort of calculate a buffer around that. We try to identify the amount of land that's within 1 meter of elevation above that point, and then we start doing the calculation. So all of these values, though, are based on specifically in that field. So as I mentioned, the tile drainage network is not necessarily apparent to the tool, but if you have a tile drain that runs from one field to the next, or from one landowner to the next, for example, that will be a complicating factor for the way the tool sees this. But it does identify many opportunities just in this small view here for us to look at. But the important thing to remember is that bioreactors are just one practice that the ACPF produces. In its precision agricultural practices, it's got a full suite, and we've talked about most of them now. Nutrient reduction wetlands, the water and sediment control basins, the riparian buffers, grassed waterways, all of those can be used in conjunction to accomplish watershed-wide nutrient reduction and water quantity goals. So as we normally do, we don't look at these things just in a field by field. That's the one beauty of the ACPF. We were looking at this across the entire watershed. In this specific instance, we identified 178 bioreactor sites potentially that could potentially treat 9,000 acres at the cost of 46 acres of land. And that land could actually be in non-crop producing use right now. But issues of cost and site suitability, the existing easements that may or may not be on the land, the tool is oblivious to that. So these things need to be reviewed and vetted by, again, humans. So that was a pretty swift flow through all of these, but the important things to remember are that ACPF can allow you to identify watershed-wide opportunities. It is a way to work with your local stakeholders. It does provide some rigor and validity to use to hopefully obtain further funding from other sources. And most importantly, it saves time and resources. Whenever you're talking to landowners, you can say these, your land may be suitable for these various practices. Have you ever considered them? And working together as a community, you hopefully will be able to find the most number of suitable practices to accomplish your goals. So there's a lot more information about ACPF available on the ACPF website. There's videos, there's texts, there are trainings that you can sign up for. There's a wealth of information. I really suggest that you visit acpfforwatersheds.org. If you have any further questions specifically about Ohio, our vendor, Heartland GIS, and I would be glad to talk to you about this, about ACPF and its uses for as long as you'd like. This has really been very enjoyable for me to learn all of this, and I appreciate you all spending your time listening to me talk about it. And that should do it for me, Steph. Thank you very much, everybody. And if you have any questions, I'd be glad to help out.
Thank you so much, August, for the great presentation. I did put in the chat a form for you to evaluate this program and to give us feedback. And I also put the link to register for September 29th. August, we do have a question. The question is, how widely or outside of Ohio is the tool populated with data necessary to run the tool? And this is, for example, in Pennsylvania.
Well, that's a good question. I don't know. I have focused mostly on, so the tool was originally developed and implemented in the upper Mississippi River watersheds in Minnesota and Iowa. It has grown over time to the east through Illinois, Indiana, and into Ohio, mostly because the landscapes are similar, but whether it has reached Pennsylvania, I can't really say. I do know that I've heard discussions of using ACPF in North Carolina, but I'm sorry, I can't answer that one suitably.
We have another question.
All right.
And we can get back to the person who asked the question about Pennsylvania. We can research that for you. But for the next question, do bioreactors reduce sedimentation as well? Do they work to reduce phosphorus load in the tile drainage outflows?
So I think the main answer there is no, but the main way that bioreactors work is to treat the flowing water. And one of the reasons why we have to, they have a limited lifespan is this contamination from siltation. So as they carry suspended sediments into the reactor basin, some does get trapped and eventually we'll fill it up, but that's not really the sort of purpose behind what we're trying to do. That being said, capturing sediment is one of the ways that phosphorus is reduced by the denitrification bioreactors, because there is a portion of phosphorus that's bound to soil, and if you can trap that soil, then you can trap that phosphorus. Dissolved reactive phosphorus or any non-attached phosphorus is free to pass through untreated. Now, I did see in preparing for this some various experiments that people were doing where you might tie a chain of these together and have the water go through a nitrate reduction and a phosphorus reduction. You use basically the same process, just different ingredients in the matrix, so that the filter would, you just change the thing that catches the phosphorus. You'll have the thing that catches the nitrates, and at the end you would then have both reduced instead of just the nitrates. But again, a similar process would mean that you would have to have a separate bed for each one of those, and that takes up land and increases cost. But as far as I understand it, it's possible to do.
Okay, I don't see any more questions in the chat. So if you do have a question and you haven't put it there, you are free to type it. And August, we will do our best to answer. If you don't have any questions, but you just like to stay around and chat with August, I think that him and I are both available to do that here. We just want to thank everyone for coming. We're kind of officially end of our time for a half an hour lunch and learn. So we appreciate your attendance. If you haven't got a chance to do it yet, please click on in the chat. I have put a forms there. It's an evaluation, and we always appreciate you filling that out. And I hope everyone has a fabulous day.